Okay, so kinetics. It is the study of the rate which reactants, so our reactants, are converted to products during that course of chemical reaction. And the factors include temperature, pressure, concentration, and catalyst and surface area. And then the sequence of the steps or the mechanism which we believe occurs when reactants are converted to products. So that is everything that will be in chemical kinetics. The four factors that affect the rates of reactants and that we're going to look at in lab are temperature, concentration, and under concentration is also pressure, if we're talking about gases. Surface area, and addition of catalysts. So some of those, all of those we're going to look at in lab, and we're going to see what happens, what does it do to the reaction when we mess with those four different things. It's really hot in here today. Okay, everybody good? All right, so for a chemical reaction, its rate or rate of reaction expressed in terms on how fast the concentration of a substance changes in the course of a chemical reaction. So for rates of a car, how would you determine the rate of a car?
Speed.
How? Distance over time. But the change in distance over time, okay? So that's what we're going to be doing here. We're going to look at the rate of the reaction. Oops. The rate of a reaction, and we're going to look at the change of product over time, concentrations of product, and the rate of the reaction and the change of reactants over time. But something we notice here is when we're looking at reactants, it's negative. So why is it negative? Why do we have a negative there? Because they're being used up. Okay, you don't have a negative rate, but we're showing that it's negative because it's being used up. And this is the one that we're going to focus on during this unit. We're going to talk about the concentration of reactants. Again, back from pre-AP, you should remember that the brackets mean concentration or molarity. And remember, you won't have a negative rate. Okay, so here what we want to look at is this reaction. And we're going to look at the ratio of the rates. And so if we're looking at, say, N2O5, as two N2O5s are disappearing, what is happening to NO2s? You get four of them, so what happens to the rate? Or we get twice as much, right? What about an oxygen? As two N2O5s disappear, what happens to oxygen? It gets 1/2, okay? So oxygen appears at half as fast as what N2O5 is disappearing. So we want to look at this in relationship to each other. So what we can do is we can take the rates, and we're going to look at the rate in respect to N2O5. Concentration of N2O5 over time. So how can I make the rates of N2O5 the same or how can I make NO2 rate the same as N2O5? What do I need to do? If this is 2 and this is 4, what would I need to do to get them to be equal? What would I have to do to NO2's rate to make it equal the same as N2O5? Huh? Half it? Yeah, we would have to half it. Yes. We don't make rates negative. But we're just saying as this one's disappearing, this one is appearing.
So you're going to do absolute?
You can do absolute, yes. And then what would we have to do to oxygen to make oxygen's rate the same as N2O5's rate? We would have to double it. Okay, and you see that this is what we've done here. So this one would have to be half as much, and this one would have to be twice as much for it to be the same rate as N2O5. So we are making these equal rates. Now those numbers might change if we were to do in respect to NO2. But you have to look at who you're looking in respect to. Okay. So what we want to do is, using this information, we want to write a rate law. So a rate law is written as the following. It is rate is equal to K, and K is the rate constant. And that is going to be times the concentration of your reactant Okay, if there's more than one reactant there, you can have reactant A and reactant B. And it's going to be raised to the power, to a certain power, and we call this an order. Okay, so M or X and Y here represent the order of the reaction in respect to that reactant. And that is going to be the coefficient that is in front of that reactant. Okay, so these things are experimentally determined. You have to go into the lab to do it, or somebody has given you the information. They're experimentally determined. Okay, so let's do a, do I have that in there twice? Okay, so here's a hypothetical reaction. 2A plus NB produces QC plus RD. I want you to tell me what are the coefficients of N, Q, and R. So to determine this, you have what your delta concentration of A over time is, and you have it for B, C, and D. So what I want to do is I know that the first coefficient in front of A is 2. So if I look, I want to look in respect to A to B. What happens to the rate when I go from A to B? It triples. So then that means, what does N have to be? If A is 2, so it would be 6. Now, let's look in respect to, I like to do easy math. Let's look at B to C. What happens when I go from B to C? Huh? Half. It's 1/2. So we've divided it by 2. We've divided N by 2, which means what does Q have to be? If N is 6 and we divide it by 2, Q has to be 3. And then what if we go from A to D? What happens from A to D? It's divided by 2. So 2 divided by 2 means that R has to be what number? Has to be 1. I was just comparing it to make my math easy. If we know that, well, no, well, look if we did C and D. D is a third of C, right? So we would take 3 and divide it by 3, and we would get 1. You should get the same answer. Yes. Okay? All right, so rate mechanisms or reaction mechanisms. Reaction mechanisms. This is going to be our first way to find the rate law. And so there's a little bit of information in here. If you need to go back and look at this information, then it's here for you to go back. But I just want to go ahead and jump into it. Go ahead and do one of these problems. All right, so we have the following reaction. H2O2 plus 2I minus plus 2H positive produces I2 plus 2H2O. So this is what we call the Cliff Notes. This is the overall reaction. It doesn't tell us anything about how many steps it took or what was the fast step or what was the slow step. All it tells us is overall what happened, the overall reaction. Now, if you look beneath it, this is the mechanism for this reaction. You see, this reaction, that Cliff Notes, takes place over 3 reactions. And there are several different, each step has a different rate. You have slow rate and you have too fast. So the very first question I want you to do, or I want you to look at, is, I don't know if you were taught it in pre-AP, we need to make sure that this reaction matches the one that they've given us. Does anybody remember how to do that? How to write this overall reaction? Huh? Okay, so the first thing you're going to do is, if it appears on the reactant side and it appears on the product side, it can cross out. So who can cross out? H2O2, can it cross out? It's a reactant. Is there a product of it? No. I minus, it's a reactant. Is there a product? No. HOI, I'm going to the second line. HOI, HOI, it's a reactant. Is there a product? So we can cross them out. I. We already talked about I. Going down to your next line. The hydroxide, there's two of them. Can we cross it out?
Do coefficients matter?
Yes. Well, there's two. But look up there. Look and see. We have one in step 1 and one in step 2. So both of them can get crossed out. And then we have the H plus. Can we cross anything else out? Yes? What?
Wait,
No. Okay, so write your reaction. What's left over? H2O2 plus 2I minus plus 2H plus produces I2 plus 2H2O. Does that match our Cliff Notes up above? Yes. Good. Okay, so the next thing we want to do, once we've figured out that everything looks okay, we want to answer the question, what species are intermediates in the above mechanism and what are catalysts? So can you tell me, what do you think an intermediate would be? A stage between. Okay, so what we talk about intermediates, these are produced in the reaction and used up. So is there anything in that overall mechanism which is produced and then used up? What is it? Hoi and OH minus? Okay. So Hoi and OH minus. What about catalyst? Going back to your AP Bio, what is a catalyst? Okay, speeds up the reaction. So what a catalyst is compared to an intermediate, catalysts are added to the mechanism at some point, either at the beginning or at the end, and then they are spit out at the end. But those are two different iodines, though. You have the I minus and you have I2. So those are two different things. So do we have any catalysts? I would say no catalysts. Questions on that? So intermediate versus catalyst. Intermediate's made and used up. A catalyst is put into the mechanism at some point and is spit out at the end.
So if we see anything in a product that's at the very last reaction as a catalyst, in any of the products, or just the first one?
It would be...
I mean, reacted and then... Alright, sorry. If there are any at the beginning, like in the reactants, if they appear in any of the reactants and they're in the very last product, it's a catalyst, regardless of the stage?
They're at the end and they're in the
The final one.
no, they're not in the final one. They're spit out at the end. Yes, that would. You're right. If we would have put in Hoi, or which one do we have? We don't have one that we could do. We're going to see one here in a minute. Okay. So what it wants us to do is sketch an energy profile. You guys remember what energy profiles look like? Something like that. Maybe like that. Okay, so that's an energy profile. It wants us to just sketch an energy profile. We don't have any other information if it's endothermic or exothermic, but we want to look at these and label the rate determining step in the diagram. So if we are talking about humps, we have slow, fast, fast. Who's going to have the biggest hump? Who needs the most energy to get going? The slow or fast? Slow. So this would be, look, something like that. All right. The rate determining step, I'm going to say RDS. Rate determining step is going to be the one that takes the most energy. It's the slowest one. Why does the slow one determine how fast our reaction is going to go? If you're in traffic, you can only go as fast as whoever's in front of you, right? Even though you want to go as fast as you can, somebody in front of you is going to hold you up. So you're only as fast as your slowest car? No. Okay, so that is what an energy diagram would look like, and we wouldn't have any other information there. All right, so the rate law is written by our slowest step. So rate law is written by our slowest step. And remember, rate is equal to K times our reactant concentration to the power of its coefficient. So our slowest step is the first one. So let's write the rate law. Rate is equal to K. Our reactant, H2O2, so times the concentration of H2O2, and it's raised to what power? 1. Times I minus, raised to the power of 1. That power is called its order. So if you have a power of 1, that means this would be first order. For both, in respect to H2O2, it is a first order. In respect to I, it is minus. It is a first order. If there would have been a 2 in front of, for the power of H2O2, it would be second order in respect to H2O2 and first order in respect to I. So the next question is, what's the overall order? The overall order is going to be the sum of all orders. So 1 plus 1 means our overall order is 2. So that is second order overall. Again, all this is in that little paragraph prior to us getting to this right here. Okay, so let's do one more problem. Everybody good with this before I change it? You need a second? I think once you go home and you do your reading and you look at this again, it starts to make sense. Okay, let's do this next one. We know what we're doing now. I don't have to sit here and walk you through it. So, what's the overall reaction of the above rate law? So tell me, what can we cross out? What can we cross out? Okay, I hear Huber. We can cross Huber out, and I heard Huber. So we're crossing Huber out. Anything else? Nope. Let's write the equation. How many HBRs do we have? 4 HBr plus O2 produces 2 Br2 plus 2 H2O. All right, so some of those that we crossed out Huber and Hober. Which one is an intermediate? Which one is made and used up? Huber. And who's a catalyst? Who is put in there at some point and then spit out at the end? Hober. Sketch an energy profile. So how many humps is this profile going to have? 4. Who's going to be the tallest hump? The third one. So, dun, 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 dun. Rate determining step is the third one. So now you write the rate law. So tell me what is the rate law? Rate is equal to K times the concentration of HBr time to the first order times the concentration of O2 to the first order. And our overall order is what? 1 plus 1 is 2. You can write 1 there if you want to. Yeah. They're not going to count you off or anything.
So, determine order by coefficient.
In your slowest step. You cannot write a rate law by using your overall reaction. You have to use your slowest step.
So the coefficient of our slowest step determines.
Right. And then you add those 2 orders to get your overall.
So, for slowest step has a coefficient to second.
Yes. Okay. So let me tell you what order actually is. So if you have something, order just means it's based on how fast it's going to go, and it's based on your concentration. So if you have something based on a 0 order, that means that no matter how much I keep putting into the reaction's not going to speed up. Okay? If I were to take it to a first order, then that means if I double my concentration, then my reaction is going to double. So it's proportional. If I put to the second order, if I double my concentration, then my reaction is going to quadruple. Okay? Okay, so let's take a look at this next one. I'm going to do some reasoning here. It says it wants us to determine which is the answer, which mechanism is most reasonable. So what I would do for my reasoning, it says explain your reasoning. My reasoning would be me working this problem out. So my first thing is I'm just going to write the orders. So A does not have a fast or a slow, which means that this takes place in one reaction. So the rate would be K, and this time NO2 is to what order? Second. And then we have F2 to a first order. Does that look like the one that they have given to us does that look like the one I've circled? No, so that answer is not right. I go to the next one, and I go to the slow one, and we write rate is equal to K NO2 to the first power and F to the first power. Does that look like the one that they've given us? No, why not? F is not a 2. And then if we go to the next one, rate is equal to K NO2 to the first power times F2 to the first power. Does that look like it? And that would be yes. That would be our reasoning. Yes?
Sorry, why are we looking at the slow one?
The slow, because you're only as fast as your weakest link or the fastest car in front of you. Okay? Marcus, what are you doing over there? Okay, we'll quit. You're being loud. Okay, last problem, and I'm done.
You said the double.
This one's really easy. When a certain substance's concentration is doubled, so when the concentration is doubled, the initial rate proceeds 8 times as fast. What is the order? So some of you can probably just look at this and come up with the order. But those of you who can't, this is what you are going to do. Is first of all, write the skeleton of your rate law. Rate is equal to K times the concentration of whatever you have to that power, X. We don't know what X is. That's what we're looking for. So if our rate was 1 and A was 1, then that means this would be so that's what we're going to look at it. So they're both starting at 1. If rate is 1 and A is 1. What if we double A? What does it say? We says we doubled our concentration. What happened to our rate? But look at the question. It says the initial rate of the reaction proceeds 8 times as fast. So rate is now equal to 8. So what is the value of X? 3. So what order would this be? This would be third order. Okay? So get that skeleton and be able to write that when you start looking at things like that. Are there any questions? So your homework is that first page.